guys, I'm going to talk to you a little bit today about an amazing paper that came out at a conference in June of 2021 entitled An Image is Worth 16 by 16 Words, Transformers for Image Recognition at Scale. This paper, written by the authors you see here, was really monumental in introducing the utility of transformers, which were formerly used for NLP or natural language processing tasks that for a long time researchers have been trying to utilize for computer vision tasks or image recognition, but have been pretty limited in the scope of its utility. So the authors of this paper talk about how the convolutional neural networks in natural language processing have always been challenging until the original transformer was created, introduced in a paper in 2017 called Attention is All You Need. And they discuss how that was really revolutionary for the world of natural language processing and why it's been so difficult to apply that to computer vision tasks or to object recognition tests, such as the image you see, like recognizing that these are tree trunks or sawed-off tree trunks or several different sizes of sawed-off tree trunks. And it's always been typically a scaling problem, like larger data sets versus smaller data sets have proposed different variability and success in utilizing these transformers for computer vision. So far to date, before the paper was released, ResNet has been the kind of mainstay architecture that has been used most widely in computer vision. And then they talk about the difference of using convolutional neural networks and transformers, and ResNet uses a slight combination of the two. And then they talk about how their model performs, and they compare it to ResNet and to a few other kind of mainstay architectures in the field. And then they talk about its scalability and its utility, both at and its global reach and also its scalability for smaller data sets. So since ResNet was trained on a very large data set, and typically that's been the most successful types of data sets out there, it's been difficult to find something that works for both large and small data sets. And so the authors of this article were able to finally put something together in the vision transformer called VIT that is able to do both. So it's they talk about all of the foundational attempts to get where they are now. The first one back in actually it's over a course of a few years, starting in 2018, using local multi-head dot production self-attention blocks. We'll talk about what the architecture of a transformer is, just to review, and how those have been used. They've been useful for only very, very local applications in computer vision. Then there were sparse transformers to be able to introduce some semblance of scalability and globalization, and then small patches of 2 by 2 pixels had been useful for very small resolution images. But again, they came up against the problem of complexity because it would be really hard on computational performance and complexity. So the most another I don't want to say most, but another really successful one up to date had been the IGPT or Image GPT, which had combined transformers and convolutional neural networks with the caveat of making sure the images are scaled first. And then the authors are proposing how using transformers via the vision transformer on large scale data sets are commutative for both global and small scale applications for state of the art performance, the best up to date. So this is an image, just a review about what a transformer is. This is an image from where one of the first papers that were out on the market presenting how transformers work. So you see the three different colors based on two different outputs. So the three different colors represent the query, the key, and the value. And the query is well, I'm going to just go through these for you. Efficiency. Well, okay. The result of this transformer, the efficiency improved to a linear. So basically, what it does is it takes the positional encoding of where this is from an NLP perspective. So basically, like where a word is in a sentence, like the dog chased the cat. So where the dog is in the sentence gets a positional encoding. So we might call this in English like the subject of the sentence. And then the it'll also get a semantic encoding, which is what are the different the different definitions of the word dog. So you could say somebody dogs somebody, like they're giving somebody a hard time, or it's an animal, it's a dog, it's a canine, or et cetera, et cetera. So there are different uses, at least in America, of the word dog. And so based on the semantic meanings of the word dog and the position of the dog being in the dog chased the cat in the sentence, well then we know that the dog, a person dogs somebody else is not going to be that positional encoding for that would be as a verb. So it would not be in the same position as the dog chased the cat in a sentence, contextually speaking. So it's going to go down a different path right away based on that positional encoding. So, and then it takes it a further step by being able to do that at a larger scale of paragraphs and actually a whole corpus or a whole document to be able to understand what the context of the story is about the dog chasing the cat. So then if you ever want to talk about, if you want to submit a query and ask, well, is this about somebody giving somebody a hard time? Well, for sure it's going to say no, because the whole rest of the document is also informing it through these positional and semantic encodings so that it knows for a fact that the dog, when talked about dog in the document, we're talking about a canine. So it does that through this flattening three-value tensor, and it's flattened into a vector numerically, so that you have one line of numbers that represent all three of these, the key query and value. And so you get a linear input into a neural network, and then that neural network, its output, it keeps propagating in the key query value sequence, and it also retains some of the information because of the positional encoding. It retains some of the information that it was fed. So this is what was really so monumental for the transformer, because up until then we've never had a way to kind of track what's been getting talked about when it comes to natural language processing. So it's kind of like putting a tag on the conversation, a semantic tag, so that we now are able to get some kind of context. So the self-attention mechanism is what they refer to when they're talking about kind of hanging on to those previous meanings in a conversation, so that you're able to retain the context. Self-attention mechanism is kind of the metric of measuring. Well, if you're talking about um, somebody giving somebody a hard time, well, so far it knows that we've been talking about a canine, so it's going to be um, the self attention mechanism is going to be the one that kind of casts some doubt that you're trying to divert the conversation to something else. So it uses by the use of these sequential positions, it places those positions both in the encoding and the decoding layers, which is what it's getting fed, and then what the output where what the output delivers, so that it's getting stacked layers, so that were the conversation to move into something else eventually, but it will take some time, some reiterations, uh, some further cosine similarity in order for that, some more connectedness for that conversation to move. So basically, what it's doing is it is decreasing the depth of all the layers, so that it's having to require it's no longer having to require so much iteration, but it's more connectedness. So I basically picture a bunch of furry hairballs all connected together, because all the ends of the fibers of each little hairball can go anywhere, but by understanding the connection of where we've come so far, by the third and fourth little fuzzball, we're able to know the string of what we're trying to say, the fibers that are being connected, so that we're getting our context overall. So this is a graphic of the scale dot product attention, um, and trying to give you some semblance of how that comes out of the multi-head attention. So multi-head is there are several different neural net. Well, so several different neurons. They're all getting fed linear vectors, and um, I need to move on. There are better ways to describe this, and I encourage you to keep on looking for more depth and explanations as I need to get to the point. So the transformer, just to remind you, was introduced from the Attention Is All You Need paper. It introduced the encoder and the decoder stacks, the scaled dot product attention, scaled meaning between 0 and 1, and then the dot product is the dot product between the key, the query, and the value matrices, and then the multi-head attention is basically stacks of those, and the position-wide feed-forward networks means there's always a tag of the relative position and the absolute position of where the topic basically is within that string of connected sentences or conversation back and forths, or paragraph and a corpus, etc., etc. So it's basically the tracing of the topic. The embeddings and the softmax is the output for each of the heads, and the embeddings are the tokenized tensors, the positional encodings, that tag we talked about, and the self-attention mechanism. That was what was so revolutionary for the transformer. So the self-attention mechanism, by retaining the positional encoding, basically this was allowing us to, if there was ever a connection, because before with the convolutional neural networks, everything was sequential. So if there was ever a feed-forward mechanism that basically the stochastic gradient descent, attempting to find the semantic or the cosine dissimilarity or similarity between the topics, if there's ever some kind of a vanishing gradient in those, then those would kind of get caught up in a recursive infinite loop. So the self-attention mechanism basically was a short circuit for that, so that if that ever happened, we were able to go back and retain where we were just at, and continue looking. So that's what's been so monumental and revolutionary about this mechanism in NLP so far, and it's been used in these really monumental tools that we have nowadays, like ChatGPT, BERT, etc. And now we're able to apply this to computer vision. So, computer vision, what's so cool about the vision part is that it produces an image as a sequence. That's a grid of patches. So a patch is a n by n square, based on however many pixels you want to make it. And then the patch embeddings are basically vectorizing that patch. So you take the 2D image of, like, say, a 3 by 3 square, and those squares all represent numbers or pixels. And then, just like words were tokenized before, now we're vectorizing those patches. So positional encoding is just like the thing from the NLP, the transformer in the NLP. It's the same thing. It allows us a localization tag of where this particular pixel is related to the rest of the image. So it's that relationship that it's able to retain as it feeds forward. So the vision transformer inputs the image as a patch of 16 by 16 pixels. It's flattened and linear projected with the position encoded. It feeds forward the flattened vectors into the transformer encoder, several layers with multi-head self-attention, just like the NLP transformer. And then, just like BERT NLP, the vision transformer introduces a class token to the sequence, and this is learned during training. This basically follows it around during training in order to finalize its prediction, like, this is a dog, this is a cat, this is a car, etc., etc. That's the class. The final layer's output corresponding to the class token is then finally passed through the classification head. So during training, the class is given a number as its particular assignment, and then the classification is through the maximum probability at the end if it's a soft mix. So here's the visual from the paper, where they introduced the vision transformer. See how the end at the top left, it's called class, where this is a bird or a ball or a car. That's an object recognition. The MLP head is what you are. It's the multi-layer perceptron that you are able to define your classification tasks, and then that is all coming from the transformer encoder. And everything under that is basically mimicking the NLP process. So the biggest difference for this paper is that the authors were able to prove that we're able to use exclusively transformers and not involve convolutional neural networks anymore, and that it's completely scalable on both large scale and small scale data sets. So they gave some examples. So these are four examples, very small examples, to show how they utilize the visual transformer. And we have the dog, the airplane, the hopscotch, but it's like kind of like specialized with the keyhole drawing, the chalk, and then the dude playing the instrument, the trumpet. So these are all object recognition tasks that we want to isolate the focus or the subject of of the object from the background to be able to recognize what it is. So using the visual transformer, these created basically maps. So everything that you see that's highlighted is mapping the subject and what it is, so that it's able to say that we have what's given the attention in the photo is the dog, and is the airplane, and is the keyhole on the hopscotch, and then is the guy playing the trumpet. So it's able to isolate those things from the background and only visually acknowledge what the subject is, to be able to recognize exactly what that is and compare that to its database. So when the visual transformer was tested against these other mainstay models that we've had working so far, it outperformed all three of those models. So you see on the left, the VIT-H14 is the visual transformer trained on the hugest data set. And 14, I forgot what 14 means. I think it's 14. No, I don't want to misspeak. But it was that versus the 16. And then we had the I can't remember what all these encodings mean, because that's what everybody has to put acronyms and everything. So anyway, these have been the benchmarks that we've been using so far up until now. And you can tell that our best one up to date was the VIT-L, right to the right of the VIT one. It had been the best to date because of the 287% and the 63. It was the most consistent compared to the other two previous models, where you had a larger disparity between the 70-something percent and the 80-something percent. So the BIT was the best to date that was trained on with the ResNet CNN approach, and our new transformer model performed better on the natural types of training, which is object recognition sets, which are like huge, massive data sets of like, this is a dog, this is a cat, this is a school or a car. Those are natural, and then specialized are medical and satellite imagery. So that's like topographical stuff. Also, like this looks like it would be a tumor within a rib cage or something. That's all specialized. So it's like specifically like, we're going to give you a data set, and then when you find anomalies, you're going to let us know. And then the structured is the geometric localization tasks. So those are more like cosine similarity processes. Those have been a lot more challenging for all the different methods so far, and it's ours is no less, but it's still better than the other guys. So that's what I was just trying to show you. So all in all, the visual transformer has been pre-trained on really large data sets. So it's a way computationally faster because of the parallelization that and the computational efficiency that it achieves when compared to those other benchmark models. So it already achieved those results in only 3 days, and using the same processors on all of the other models, up to 8 days. It's still, those other models had underperformed still even after a longer time. So the great thing is that the visual transformer it's been really proving itself to be much more efficient computationally, and then it's also much more robust in regards to what it's been able to learn based on its billions of data sets given to it. So And what's amazing is that really all you have to do, like, because it kind of has this background of having learned so much on these previous images, you can use it for transfer learning applications, so that all you basically have to do is peel off the top layer for your classification tasks and slap a new one on, and you have all of that data behind you to give you an informed model with weights, pre-trained weights, so that it's still going to give you a really good output um, because of its global context. So finally, the other great thing that's so amazing about this is that it's scalable. So um, just like we talked about the medical and satellite imagery and stuff, you can use the visual transformer for specialized tasks uh, by just peeling off that top layer and changing your classification output. Uh, it can still train based on its combination of transformers. It can still train itself using for anomalies and things using your data. So it's a really versatile blend of uh, able to be trained and then already pre-trained. So that's what's so really cool about this visual transformer, because it's really just in the architecture and the structure of where its power lies, not just in its knowledge of um, the data sets that it's been tested on before, even though those are still out there and they offer really great tools for transfer learning. So thank you so much for hanging out and for listening to what I got to say about what I understand this summary to say. And I encourage you to go check out the paper for yourself. And it's a really fascinating read and really exciting about all the strides we're making in the world of computer vision. Thanks a lot.